contain two terms sine, then the control of fractional sine maps. I represent three controllers to stabilize the two maps. The third is synchronize the two maps, then conclusion and inferences. So, introduction. Recently, research concluded that fractional maps have similar form but hold rich dynamics than their counterparts. The fractional sine map obtained by simply replacing the x-squared term in the standard Riemann map by the trigonometric sine term. When talking about chaotic system, it is imperative that we talk about stabilization and synchronization. The stabilization is adding a controller to the state vector of chaotic map in order to force its state to the zero asymptotically as time progress. Synchronization is the add controller to the snake system to follow the exact trajectory of the master system from a different initial point in phase space. In this work, we represent three controllers. The first one is stabilize the two maps, two sine maps. The first is the sine map. The second is the sine map. I mean, have two times sine. Then the third controller is synchronize the two systems, the sine map and the sine map. Okay. Then we verify the finding by a numerical simulation or preliminaries. In this section, I present two definitions. The first one is to give an overview of the sum of an arbitrary function for the fractional sum given by 1. And the second is to give an overview of the new Caputo type delta difference of a function x given by 3. Then two theorems. The first theorem is given the numerical solution of a fractional system given by 4. So the equivalence discrete integral equation can be obtained as 5, where x naught is the initial condition given by 6. Theorem 2 is the theorem of stability. Given a vector value function x, A nu is the fractional order is belongs 0, 1. It is a matrix, and T is the time or parameter. The zero equilibrium system, the zero equilibrium of the system 7 is asymptotically stable if the engine value of A is belong this set. Okay. Then we move to the fractional sine map. In this section, I represent the fractional sine map. I repeat, the fractional sine map is obtained by replacing the x square in the Riemann map by the sine term. Okay. In this section, we represent this system by the Caputo derivative. Okay. For numerical analysis proposed, we employ theorem 1 to obtain the numerical solution given by this. The discrete kernel function can be simplified, taken as this formula. The numerical simulation for showing the bifurcation diagram for three various values of the order nu, shown in figure 1. We consider the same bifurcation parameter to plot the phase portrait or the factor shown in figure 2. Then we plot in also the largest diagonal exponent in figure 3 to confirm the chaotic behavior of the system of the sine map. Okay, this is the bifurcation diagram of sine map with different fractional order of nu. We see the chaotic behavior.
Sorry, okay.
Alpha, as it من 1 كانت عندنا 2.8 على الكاوتشيك كده شغل باش نشوفوا عامل قداش من جهه دكتور هنا the attractor of fractional sine wave for different fractional nu. This is confirm also the chaotic behavior. Here the attractor is a strange attractor. Okay, it is a strange attractor. So the sine map it is chaotic system. Then the largest level of experiment for two parameters alpha 3 and beta 0 or 3. So here we see, I explain this also. Here lambda max is the largest level of experiment. The largest level of experiment is positive. So in the fractional discrete system, if the largest level of experiment is positive, so the system is chaotic. This is a really good tool to confirm the chaotic behavior of any system. Then we move to sine map. Now we move to a new 2D chaotic map that includes two sine terms, as we see, sine x minus 2 sine y. The so-called sine map, similar to the previous section, using fractional discrete calculus notation described in preliminaries. And here I mean theorem 1 to extract the numerical solution. You can write the fractional sine map as follows and the numerical solution as follows. Using numerical formula for plotting the attraction and the propagation diagram and the largest Lyapunov exponent for two value of the order. So this is the attractor of what? Of the sine map. Attractor كبيرة في الساين ماب ما كانش دوبلي كيفاه. صح؟ هنا نشوفوا شغل دوبل ها. ومن بعد دونك هنا شو نلاحظ إنه ساين تيرم هذا عطى more rich of chaotic. Okay. Then the largest level of exponent, it is clear it is positive. So this is the bifurcation diagram of fractional sine map with the nu as critical parameter for two different initial conditions. The red one, it is x naught y naught equals -1 -1, the red one, and the blue one, it is 1 1. Okay. Stabilization control of the fractional sine map. So here theorem 3 and theorem 4 given the controller which stabilize the state of the sine map and sine map. First we design an active controller with the aim of stabilization the fractional sine map as well as the fractional sine map. In general, stabilization control problem is concerned with finding suitable adaptive control law such that all of the system states converge towards zero asymptotically. Theorem: the 2D fractional sine map can be controlled under the 1D control law. So it is a system in 2D. I control it by controller in 1D. The result of the simulation confirms the successful of the proposed law in stabilizing the system states asymptotically. So here. controller كان عندنا سيستم هذا هو ساين ماب نفس الشيء الساين ماب احنا نشرحها طبعا احنا نزيدوا كنترولر باش نحاولوا نراجعوا للصفر نحاولوا نستبدلوا للصفر نزيدوا لها كنترولر صحيح شتي لي تيرم اللي ما نحتاجهمش اللي يخرجوا لي لي فالور بروبر تاع لا ماتريس اللي طلبوني نحاول نحيي ونيجليجيهم الكل باش هذوك تكون عندي لا فالور بروبر لي فالور بروبر تاع الهنجينيه لا فالور بروبر لازم يكونوا في الستيت هذيك تاع ويك صح؟
علاش صافي دور؟ مثلا هي تسمى دور كونتر تخيل دور علاش صافي دور؟
هي ابيسمون ناقص لي في الكوب بالعكس هذه بيان في
تنقص الكوب زعما فوق شو الكوب
اكيد وهنا هذه هي البيان في خاطر تقدر مثلا واحد سيستم يكون اوتوماتيك تخيلوا انت كنترولر تكونتروليه بكل معناها احسن حاجه شيء انك تكونترولي زوز والاخر يمشي وحده معاك شغل بالعكس هذه ميرفي get our result, let us define what we mean by synchronization. The synchronization error given by خلينا complete synchronization لأن هي أقرب للواقع. The master-slave pair is said to be synchronized if the error gives to the zero when the time is exploded. Okay? Theorem: the master-slave pair system can be synchronized subject to this two controller. So as we see, the control U2 is equal to 0. So 2D control by control in 1D. In order to ensure the success of the proposed remote